Our next module is on waves and wave motion and how energy travels through waves. A lot of the information in this first section, if you have had a good physical science course, may very well be review. So if you have had a good physical science course, again, you may not spend a lot of time on this. I do, however, want to make clear that even though your homework assignments do not have a lot of questions on the parts of a wave or how wavelength is measured or frequency or anything like that, I do want to be sure that you understand that on your test, I do expect you to know the material that I'm going to be presenting here today. Don't be surprised if there's a wave, diagram of a wave on your test, and I ask you to label the different parts of that wave. So make sure that you understand all of this material. Like I said, even though you're not going to have a lot of homework questions from the book on this particular material. So there are two basic types of waves that we usually talk about. One is called a transverse wave, and the other is called a longitudinal wave. A transverse wave is what you normally think of when you think of a wave. You think of water waves that, if you're at the beach, they will come crashing into the shore. If you take a rope and you jiggle it up and down like this, then you're going to see a wave go through it. And so that particular wave, again, is called a transverse wave. And transverse waves are the same kind of waves that light waves consist of, okay? So if I look at this diagram of a wave, if there was no energy moving through this particular medium, this dotted line in the middle would be the rest position, so there would be no movement. Everything would be laying flat across that line. This is called the crest of the wave, and this is called the trough. And the distance between the crest and the rest position is called the amplitude. And it would also be the case that you would have the same distance between the rest position and the trough. That would also be classified as the amplitude. Both of those are the amplitude. And the amplitude gives us information as to how much energy a wave is carrying. So the taller the wave, the more energy it has. If you think about ocean waves as they come crashing into the shore, you're not going to have a surfer who's going to be trying to ride a 100-foot high wave. That would be way too dangerous. So the higher the wave, the higher the amplitude, the more energy the wave has. If we say that the direction of wave travel is, in this case, off to would be your right. As the wave is traveling that direction, your particles are actually going to oscillate up and down this direction like this. So this is called oscillation. And if you think about this, if you think about a rubber duck that would be sitting on a water wave, as the wave is moving through the water, the duck is going to be bouncing up and down like this. He doesn't necessarily get carried this direction. He tends to bounce up and down instead. Okay, you see that in your bathtub. If you're taking a bath and you're kind of moving around in the water, the duck tends to bob up and down. He doesn't tend to really go flying off one direction or the other so much. Okay, so the other type of wave is a longitudinal wave. And the best way to think about this longitudinal wave is if you take a slinky and you have it stretched out on the table and you kind of jiggle it like this to make the slinky move back and forth. I would assume that probably most of you have played with the slinky at some point in your life. I did send you some links to a few other videos where they show you again, using a slinky, what a transverse wave looks like, what a longitudinal wave looks like using that slinky. So if you're having trouble visualizing that, make sure you check out those links so that you can see some examples of what this looks like using a slinky. In a longitudinal wave, what happens is that the material bunches up and then it spreads out, and then it bunches up and then it spreads out. So while we had a crest in a transverse wave, in a longitudinal wave, a crest is instead referred to as a compression. because the pieces of the slinky would be close together. The trough in a transverse wave is analogous to a rarefaction in a longitudinal wave. Okay, and just like up here, where if I want to measure the wavelength, I would go from one crest to another crest, or from one trough to another trough. That would be the wavelength of the wave. And we often abbreviate that with the lowercase letter lambda. And similarly, in a longitudinal wave, I would be going from the middle of one compression to the middle of another compression to measure that wavelength. Okay. Now, when we talk about the frequency of a wave, the frequency is how many waves pass a certain point in a certain time period. And the most common unit of measure for frequency of a wave is the hertz, and that is the number of waves per second. So you're going to see it abbreviated as an Hz, or you're going to see it, the units, as 1/seconds, because it's going to be how many waves pass by in a second. All right, when you have a longitudinal wave, now here I said if the wave is traveling this way, your particles are going to be bouncing up and down this direction, okay? In a longitudinal wave, if my wave is traveling this way, the particles are going to be oscillating back and forth. So the oscillation happens this direction. And so if you would think about tying maybe a little piece of string to one of the pieces on a slinky, and as that slinky is vibrating back and forth, the piece of string is going to be vibrating back and forth also. So that's an important point to keep in mind. In a transverse wave, the wave travels in one direction, but the particles are going to be oscillating perpendicular to the wave direction of travel. In a longitudinal wave, the direction of wave travel is parallel to the direction of the oscillation of the particles. Okay. Now, the one other thing that we need to hit here is wave speed. When we think about velocity, like we've been talking about it before, we've talked about how velocity is displacement over time. And when we talk about waves, he puts this formula in a slightly different format. He tends to say, I think he sets it either equal to frequency or he sets it equal to wavelength. I prefer to do it this way, to say that velocity of the wave is equal to the frequency times the wavelength. The reason I like to write it this way, it's the same equation he gives you, I've just rearranged it. I like to do it this way because then it's easier to see that as the frequency goes up, the wavelength's going to have to go down. So they're inversely proportional to one another. So if we think about units here, just like up here when we measured velocity in meters per second, that's also going to be the case here, because wavelength, if we measure it in SI units, it's going to be measured in meters, and frequency is going to be measured in hertz or 1/seconds, so that you can see if I multiply wavelength times frequency, I will get a unit of meters per second. Okay, so again, just one more quick reminder, make sure that you're familiar with all of these terms. Make sure you understand how the particles are vibrating with relationship to the direction of wave travel. And then we will go into a lot more detail about waves as we move through the chapter.